Hello everyone, welcome to your next lecture. We are going to be looking at Boolean logic and bitwise operators. We've seen some of these bitwise operators in a previous lecture, such as AND, OR, XOR, NOT. We're going to revisit them to kind of refresh our minds, and we're going to look at some new ones like left shift and right shift. So the first Boolean logic gate we're going to revisit is the AND gate, which says if you have an expression on the left and an expression on the right and they are both true, then we'll evaluate the entire expression to true. And one of the ways we can represent that is with a logic gate, and the AND logic gate looks something like this. So we have two inputs, A and B, and we have an output. And so how this relates with Python is that if we have an expression, let's say a variable x is equal to 10, y is equal to 15, and we're looking here and we're saying, okay, is x less than 15 and is y greater than 10? And so we're going to evaluate both of these expressions, and we're going to have a 1 here as this is true, a 1 here as this is true, and our output is going to be 1. And so we actually came up with a truth table the last time we looked at this gate. And so the AND truth table looks something like this. We have our input A, we have our input B, and we have our output Q. So when A is false or 0 and B is 0, our output is 0. And so all the combinations that we can have here are written out in this truth table. And they simply state that if any of the inputs are false, the whole statement evaluates to false. But if only if both statements evaluate to true, is the end result true here. Moving on, the next one to look over is the OR gate. And the OR gate states that if either input A or B is true, then the whole statement evaluates to true. And so the OR gate can be represented as this triangle-like object. So we have here our two inputs, A and B, and our output Q. And we're going to have our same truth table that we can generate, which shows us all the possible inputs and outputs that can be generated with this gate. So as always, we start out with all the possible inputs and we generate our outputs. So as we stated, the OR gate says that if A or B has an expression that evaluates to 1 or true, the output will be 1. So we see here that when they're both 0, it's 0, but for all these cases we have at least 1, and we are good to go. One of the more basic gates is the NOT gate, and we should review that as well. The NOT gate simply is a triangle with a little buffer in front of it. And so the NOT gate just kind of inverses whatever the input is. So we have one input and we have one output. So the input can either be a 0 or a 1, and in those cases the output will be 1 or 0. And you'll see this sometimes if you have an expression in code where you get a result and you want to know if it's the opposite of the result in your code. So let's say you just have a function that returns, it's called isBroken. That is your function call. So one of the ways is if you're evaluating your code, you can have an if statement to check if it's not isBroken. The next gate that's important to look at is called XOR, or exclusive OR. And this one states that if any of the two inputs are the same, the output is always going to be 0 or false. Only if the two inputs are different will the output be true. So the XOR, exclusive OR, can be represented as an OR with an extra line in the back. So we have our two inputs, we have our output, and we'll draw our truth table. We have our two inputs, we have our output, and our inputs can be any of the following. And so on our first case, both are 0, so the output is 0. In our second and third case, they are different, so the output will be 1. And then in the fourth case, they're both 1, so the output is 0. So this is cool and all, but how are we going to relate this to Python? Well, it turns out that Python has these operators. It has the AND operator, the OR operator, the exclusive OR, and the NOT. And it also has the left shift and right shift that we talked about. But they don't look like these gates in Python. So let me kind of show you what they're going to look like in your code. So we have the ampersand for AND. We have the pipe for OR. We have the caret for XOR. We have the tilde for NOT. We have two less than signs for left shift. And then we have two greater than signs for right shift. So let's kind of show you an example using binary numbers. That's when these symbols are going to work best, but they always have applications for little tricks here and there. So let's say we have two base 10 numbers. We have 75 and we have 84. And I'm going to put them into binary here. I've done this off screen, so I'm not memorizing these numbers or having it or being able to figure it out that quickly. So 75 is represented by 1001011, and 84 is represented by 1010100. All right. So I'm going to copy this real quick so I have it for future examples. But let's start with the AND gate, and I'm actually going to bring it down so we have it next to us as we work here. All right, so the AND gate tells us that only if both numbers are the same will the output be 1 or true. So let's say we wanted to AND these numbers and find out the result. We could take 75, AND it with 84, and we will get a result here. So we kind of go through it. You can start on the left, you can start on the right, whatever is more comfortable for you. I'm going to start here on the right, 1 and 0, and we know that to be 0. 1 and 0, we know that to be 0. 0 and 1, 1 and 0, 0 and 1, 0 and 0, and 1 and 1. So we've actually transformed our two numbers to create an entirely new number. And if we use our trick from what we learned previously, we know that the value of these places are 1, 2, 4, 8, 16, 32, and 64. So we actually took 75 and 84, ANDed them together, and got the result of 64. Let's verify that with Python. So if we're in Python here and we bin 75 and 84, we get OB1 with 1, 2, 3, 4, 5, 6 zeros, 1, 2, 3, 4, 5, 6 zeros in our example. This checks out. And then let's just print 75 ANDed with 84. And we get 64. That checks out. All right. So that's an example of the AND bitwise operator. So let's take a look at OR. I'm going to bring OR down as well. All right, so let's take a look at 75 or 84 here. So we're going to apply that same process. We're going to use the truth table as a guide if we don't know the answer here, and we're just going to go through and OR the bits together for each specific spot. So we get 1, 1, 1, 1, 1, 0, 1. So this one's a little trickier to do using that kind of shortcut method I used for this. It could still be done here. So we would have 64 plus 16 plus 8 plus 4 plus 2 plus 1 to get our final answer. I think that's 95, but let's go ahead and check it with Python. We're going to do the same thing here. We're going to bin 75 OR with 84. And we get 1, 0 with the rest ones. That's correct. And then we're going to print here 75 OR with 84. And we get 95. All right. So that checks out. All right, cool. Let's take a look at XOR next. I'm gonna clean this up a little bit. All right, now let's take a look at XOR here. So in this case, only if the numbers are different will the output be a 1. So we can go through here and we have 0. Oh, I'm sorry. 1, 1, 1, 1, 1, 0, 0. So let's go ahead and throw that in Python. Let me draw the caret symbol here before I continue. All right, let's check it out in Python. We're going to have bin. So the binary representation of 75 and 84. We get 1, 1, 1, 1, 1. And so the zeros are removed to the left here. But we did have 2 zeros. This checks out completely. And we're going to print 75 caret with 84. All right. 31. Pretty cool. And let's verify that here in our document. We got 1, 2, 4, 8, 16, 28, 30, and 31. All right. So the final gate we look at here is the NOT gate, which simply just... So this is what we'd actually use NOT on on a single number. So let's go ahead and do not on 75. So this is going to be interesting here. Let's just go through the example first. So we're pretty much just inversing every bit. But there's a catch here. In the previous example, these two zeros were hidden in Python. But they still exist. They're just hidden because they're not important to us. They're zeros. They have no value. However, when we use the not operator, we're inversing every bit. So let's take a look in Python and see what happens here. So we actually got a negative number. Let's print this. Oh, I didn't use the tilde. So we get negative 76. And let's go back into the paper and show you kind of what happened. And we're going to talk about why it's negative. But you have 32 bits in a number. So that's 10 of them. That's 20. That's 30. 31, 32. We had 0, 0, 1. Or let's go with what we had originally. 1, 2, 3, 4, 5, 6, 7 bits. 1, 2. So this is what our original number really looked like in Python. They kind of just hid this away from us. We don't need to know that we have a whole bunch of zeros. But when we inverse it, when we use not operator, all of these numbers are now important. And so that is the result of the not operator. And so you might be asking, okay, well, still, why is it negative? And so the answer to that, sorry for moving that so much. The answer to that is something called 2's complement. Essentially, this bit all the way on the left essentially, this bit all the way on the left here is a sign bit. When this bit is 0, it means the number is positive. When this bit is 1, it means the number is negative. So when we inverse that sign bit, we're actually turning our number into a negative number. This is a representation called 2's complement. It's a binary representation for integers. We're kind of going to look at this in a bit once we look at the shift, but I did want to show you that this is kind of why we're getting a negative number when we not the 75. We're flipping that sign bit from 0 to 1. And so the number is now a negative number, and the way we read the negative number is a bit different. And we'll get to that in a little bit in this lecture. All right, so let's finish off with some of our operators, which is the left shift and the right shift. So let's take a look at 75 again. So let's just say we're going to shift it by 1 here. We're gonna left shift the number by 1, and what that does is we get a new number here. I'm going to draw this over here. We get 1 0 0 1 0 1 1 0 here. And so let's figure out what number we've just created here. We know that this is 75, and we're going to go kind of using the mathy way. We have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 6 here. And so we kind of knew that that evaluated to 1, 2, 4, 8, 16, 32, and 64. We have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7 here. So for this example, the result will be 2 to the 6th plus 2 to the 3rd plus 2 to the 1st plus 2 to the 0. And we know that that's 75. So check this out. Let's say we take the same result here, 2 to the 7 plus 2 to the 6. Oh, I'm sorry. 2 to the 7 plus 2 to the 4 plus 2 to the 2nd plus 2 to the 1st. It is the result here. So let's just pull one of the powers of 2 out of this equation here. So we have 2 times 2 to the 6th plus 2 to the 3rd plus 2 to the 1st plus 2 to the 0. And so check this out. This is equal to this. So we can replace this whole part with 75. And we pulled 2 out, so let's put that back in. We can multiply our 75 by the 2 that we pulled out. So left shifting by 1 actually multiplies by 2. And a more general way of looking at this is that every bit you shift to the left, you're multiplying by 2 to the n. So let's show that with another example. Let's say we left shift by 3, the same number. So we have 1 0 0 1 0 1 1 0 0 0, and we use that same trick. And we will have a result of 2 to the 9 plus 2 to the 6 plus 2 to the 4 plus 2 to the 3 as our result here. Let's say we pull out 2 to the 3. We have 2 to the 3 multiplied by 2 to the 6 plus 2 to the 3 plus 2 to the 1 plus 2 to the 0 here. So we have the same 75 here, but now we're multiplying it by 2 to the 3. 2 to the 3 is 8. So we have 75 times 8 as our result, which is 600. So in general, every left shift by n is equivalent to multiplying by 2 to the power of n. So let's verify this in Python a little bit here. So let's say print 75 left shift by 1. We get 150. 75 left shift by 3, 600. And so this is a really cool way of multiplying by a power of 2. If you need to multiply by 2, 4, 8, 16, 32, left shifting is the most efficient and and kind of coolest way to perform that multiplication. It's also very quick for the processor to perform that action, and shifting it is very quick. Alright, so coming into our final operator, we have right shift. And so right shift is the exact same thing as left shift, but instead we're going to be shifting all the numbers to the right. As you can imagine, if left shift multiplied, right shift will... Let's see what's going to happen here in Python. But try to make an educated guess here. If we have... Let's say we take the number 64 and we right shift it by 1. I want you to try to guess the output here. Alright, we're going to get 32. So instead of multiplying, we're going to be dividing. So one thing that's interesting to know is we saw that when we had a 1 all the way on the left, it was a negative number. So Python uses something called logical right shift. So anytime it makes a right shift, it's going to look all the way to the left and see if it's a 1 or a 0 there, and then use that as the padding bit. So for example, let's say we only had an 8-bit number. It was 1 0 0 1 0 0 0. And let's throw one more 1 in there. So let's say we wanted to right shift this number by 2. It's first going to look here and say, okay, we have a 1 there, so we're going to put 2 1s. And we're actually going to just lose these bits. They're gonna fall off a cliff. If we were to be drawing this and there was a cliff on the edge, essentially these bits fall off and we pad it with whatever number was all the way on the left. So just like with multiplying, bit shifting to the right by n bits is equal to dividing by 2 to the n. This is another cool technique for dividing by powers of 2. It's just right shifting. You need divide by 2, right shift by 1. Divide by 4, right shift by 2. And so on and so forth. I think it's time we talk about 2's complement, and it's the way we represent binary numbers for integers in programming languages such as Python. So one of the reasons we use it is, let's say we had 32 bits 0 0 0 1. So this is 1 represented, and let's say we just use this bit as a sign bit. So I kind of lied to you guys before when I said this is simply a sign bit. It is a good indication of if it's positive or negative, but if it was strictly a sign bit, if this was a sign bit here and we put 1 for -1, well, what would happen is we would have 2 solutions for 0. So we'd have a positive 0 and a negative 0. And the way this was solved is 2's complement. And 2's complement pretty much says that if the leftmost bit is 1, then we're automatically negative, and we're going to add all the other 1s to that negative number. So let's just say we went back to our simple example. We had 8-bit. I'm going to do an example for this to make more sense here, because just kind of saying it is kind of confusing. So let's say we had, let's say we only had 8 bits in our number, and I'm going to get rid of this here. This was our whole number, and this was our kind of sign bit here. The result of this would be -128. If it was just an 8-bit number, we'd know that this symbolizes that we have a negative number and we start out with negative 128, and then we add any other ones to it. So for example, if this bit were a 1, we'd add 2 to the 0 or just 1 to that number, and we would get negative 127. If all of the values, let's say majority of the values were 1 here, we would take 128, negative 128 plus 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3, and I'm going to draw it out here. So we have 1, 2, 4, 8, 16, and 32. So that would be negative 128 plus 63 here. And the answer would be 65. And if we added this final bit in, we'd have 64, and we would have, oh, I'm sorry, that's negative 65. We would have a negative 1. So I'm going to go back to the example of inverting 75. How did we get 70? How did we get 76 there? So let's take a look. So just a quick refresher, we have 75, base 10 is 1, 0, 0, 1, 0, 1, 1 in base 2. And then if we invert that, we get 0, 1, 1, 0, 1, 0, 0. And we know here that all the ones to the left, these are all 1. So let's just keep that in the back of our mind. We know for sure their next bit is 1, and all the way through it goes to 1, so we have a negative number now. So if we put these in places, so this is a 1, and it repeats all the way to the end, which is 1 here. So we have our 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7 here. So that is 1, 2, 4, 8, 16, 32, 64, and 128. So just like the previous example, we're going to start out with negative 128. And then anywhere we have a 1, we're gonna add that to our solution. So we have plus 32, plus 16, and plus 4. So we have negative 128 plus 52, which is equal to negative 76, which is the result we got before. When we knotted our 75, we got a negative 76. And so here's kind of how what's going on behind the scenes. Unfortunately, as I was recording this lecture, I found out that Python, it doesn't show you the proper 2's complement version of the binary number when you look at a binary negative number. So really what's happening is what I had showed you here on the document. But if I tried to do a negative 76 here, essentially what it's going to do is show us 76 and then just put a negative sign all the way on the left. This is not a valid representation of the 2's complement representation of this negative 76. This isn't what the binary really is looking like. So just keep that in the back of your mind, that really Python uses 2's complement, and most programming languages use 2's complement, but I guess for simplicity's sake, Python gives you the binary representation of 76 and just kind of tacks on that negative here. Well, I know this lecture was a lot to take in. I personally didn't get all this information the first time around when I learned this, but through repeated learning and through repeated use of seeing this in code and using it and practicing with it, you'll be able to get all this stuff down no problem. So just a quick review before I end the lecture. We took a look at the logic gates again, and we used their truth tables to perform operations on two integer numbers. So we were able to AND two integer numbers, OR two integer numbers, XOR two integer numbers, and perform the NOT operation on a single integer number. We also took a look at the left shift and right shift. So left shift is a quick way to multiply by powers of 2, and right shift is a quick way to divide by powers of 2. They also have other cool operations, which I hope you'll get to see in the next lecture, with masking specific bits and performing specific operations on integers. And then finally, we took a look at the 2's complement representation of numbers, which unfortunately we found out that Python doesn't show, but it uses behind the scenes. Well, thank you for spending a little bit of your time with me. I hope you learned something today, and I hope you guys have a great day.